So maybe, yeah, just in the interest of, yeah, sorry that we could not hear earlier. So I briefly put it in that.
Yes, one second.
Yeah, sure. Take your time. Yeah.
Is sir audible? Can you hear us now?
Yes, sir. Yes, yes, sir.
Now you can hear. Yes, sir. Yes, sir.
Okay, so all of you there are able to hear. I'd like to hear now from you guys.
Is sir audible?
Can somebody say yes? If you could hear. Those who are in online.
Can you just confirm?
Hearing from you from 3 times.
Yes, yes. Now.
Fine. Okay.
So
You start from the right now. We'll make it much more doing now. Okay, we'll be talking about the application of deep learning to medical imaging. We'll have a overview followed by some of the things and pros we have been doing, followed by some concluding remarks. And we have to see, just to see how the trend is going on. The National Library of Medicine is a repository where all the medical imaging related publications are indexed. So they looking at the word machinery either in title and abstract versus either in the title and abstract. Considering something like having 500 publications was something some world has really picked up there. You could see around 2010 from 2010 for the last 24 years, this machine learning has been there. And similarly, machine learning started around, you could think of as 2017. And another trend that you could also see here is the publications, the slope is reducing. Most becoming hopefully will become flat. Not a bad thing to happen. There you could see that. So which also means now the kind of contributions that should come in this area should really be more profound, not anymore downloading it with a repository. And after one more repository, you take one more data set and apply it, and then you post the results. Doesn't work that well now. Okay, that's something I need to make a note of it. Right. So this really the deep learning, again, there are so many synonyms these days: machine learning, deep learning, artificial intelligence. No one really knows what exactly is the distinction. If you force somebody to say, we will say about definitions. About definitions will match to the left. Okay. So don't get carried away by what to call it. Should I call this machine learning? Should I call this deep learning? I get myself can tell you 3-4 definitions of when you call something as a deep learning. Okay. Whether the learning is deep or not, again that is subjective. Right. So you see a lot of companies coming here, they go into statistics, millions of dollars and all they will say. So you can trust that there is indeed a lot of things that are going on in this area. So there is no doubt about that. The impact of deep learning on our AI area of intelligence. So as I said, in the statistics, people used to call it, let's say you will call it as a logistic regression. You got kind of forecasting based on the input, what is the output. But you arrange it today now. And suppose if I am going to hire people, I would say I am looking for people who are working in machine learning. I would say, but if I am to go for funding, I would say, because they will know AI much better than everybody, including the politicians who will talking about this, then I would rather say AI. But at the end of the day, one thing you have to remember is without a solid background in mathematics, this is you cannot do something significant. These are just the names that are given, but that's very important stuff to keep in mind. So I would also interchangeably use deep learning, machine learning, and AI because none of us know what it exactly means. Right. So I guess you have gone through quite a few presentations that talk about the deep learning in computer vision. So what I thought is, since that is where most of the people will be working, I want to begin with the drawing some balance between what happens in computer vision versus what are the problems in medical imaging. Say, for example, when you talk about object detection there, here again you talk about organ detection or RADSS detection. That's the parallel that you see. The both problems at a deeper level are same, similar, if not same. Then similarly, you might detect an object there. That's one thing. You are going to do a classification there in computer vision. Here also you do disease classification, which kind of disease it is, which kind of, there might be multiple tumors, so which kind of tumor that belongs to. So that disease or injury classification will be there. And you will be doing segmentation work as well in computer vision. A very similar thing, organ segmentation or a tumor segmentation is what you would be attempting here. And there is a tracking there, and also in some in surgical environments with augmented reality and all those stuff, you might have to do some organ tracking or some object tracking. Here in medical imaging as well. So this is this is to just say that this is not altogether different. There are parallels between them. Nevertheless, there are also some unique problems associated with the data that comes from medical imaging or in general from the healthcare. Say, for example, it's not all the time the imaging data that you have there. The non-imaging data is also there. For example, the genes, the details of gene sequencing and other stuff be there, or some genetic information or the family history of that might be there. Some demographic information of the patients also might play a role in arriving at the final inferences. So how do you kind of use the imaging data with the non-imaging data? As you could say, it's not so common in computer vision. You most of the times will be dealing with images. That's something you could think as some problem you need to medical image. And similarly, some of you might be working on functional images. So to keep it at a very high level, it's like suppose if I am doing some action, in which part of the brain can I expect some stimulation to be there? So sometimes you might be knowing it from the clinical knowledge, but with the emergence of deep learning, what also has happened is I have a data. From that data, can I learn what is this data is saying about that? So it's a kind of a reverse engineering when you really not very sure from the theoretical background, and later you may validate with the theoretical kind of inferences and other stuff. But that's one kind of thing that you could look at. And again, find you have lots of data. Can you find some patterns to some diseases? That's another problem that you could think of, right? So one more thing I would like to draw your attention to is that is at a problem level. I was talking about what are the common problems and what are the problems that could be different. Now, what are the challenges that are unique to medical imaging when you are coming to a medical imaging domain? One first thing you could say is the size of your images. For example, if you look at a CT image is essentially a three-dimensional image. So the magnitude of the data, the size of the data you have is multifold here compared to the data that you would be getting with other computer vision, typical computer vision applications. So that's one challenge where you need to deal with data which is of very large size. And another thing is, can any of you recollect what is the order of the images in the ImageNet data set? I'm sure you might have come across or even might have used the ImageNet data set. Did you? Yeah. So any idea of the order of images you have? Hundreds, thousands? Thousand classes, right. Images, number of images is order of millions, correct. Something of that 20 million or that. And that is only half of that what Google has released. They in fact had annotated data and everything more than that. 300 million, yes. But here, when you say I have a very large data, annotated data set in medical imaging, don't be looking from the lens of computer vision. You would be hardly having 1,000 images. That itself is a big data set, annotated data set here. Okay, so with that limitations, you need to learn now. But again, there are few exceptions. For example, the chest X-ray imaging data set that was released is of the order of 1 million chest X-ray data set. Hardly there are 1 or 2 such data sets. The rest, you say in medical imaging, anyone working in medical imaging says that I have a big data set, then you realize that he's talking about thousands, not millions. Okay, and small sample size also, as you are saying, 300 classes and down. So here the classes also is less, and for some classes the samples that you have is even much less there. This is not working, but still I hope they are able to hear. Yeah. Okay. Yeah. Right. So again, one more thing is ImageNet. Take for example again that example of ImageNet itself. Any of us can do the labeling there. So it is not that expensive per se, because you could ask people to even it is very easy. It's a fun and it's a very easy trivial thing. But same is not the case with the annotation of the medical data and these abnormalities. So this is pretty expensive because only the clinical experts can do this. So that is one, you cannot have as much training data as you want. And even the training data is sometimes imperfect. Say there's something has been detected, let's say as a cancerous thing, unless biopsy is done, you might not be getting it. But not in all cases you have that would be doing, because it's something to deal with the humans, not just some images that you are going to deal with. And some tests are sometimes not possible, and you may not even have access to sometimes, even if the test is done. So this may eventually result in the training data being imperfect. That's also is possible. Some of the annotations themselves could be wrong, unlike the other applications. Wherever this pathology would be required, that means pathology means you need to take the tissue out and do the test, and then only you can establish the ground truth. For example, it's very easy. The doctor could, from the symptoms, more or less say he's Alzheimer's, he's having some forgetfulness is related to Alzheimer's disease. But it's not like for everyone you suspect a tissue from the brain can be taken and sent to the pathology just for saying that I am going to develop a deep learning algorithm. Okay, so that's another thing. So these challenges needs to be kept in mind when one is going to work in the area of medical imaging. Again, it has its own celebrations. Deep learning has its own celebrations in medical imaging area also, where people are able to get results that are on par in some cases with what an clinical expert will do. So that has indeed happened. Here are some of these applications. You could go to this paper for more detailed one. I think if I remember correctly, this is a Nature paper. You can go to that. So this is where mammography images telling whether a tumor in the mammographic images is a benign or malignant. They're able to get matched with what a doctor does. And this is related to lesions in the brain, multiple sclerosis they call it. There is also a very good data. This has a very good data set, by the way. This is also, you have a very good data set. They call it as BRATS data set. Every year, year after year, lots of challenges happen on the data set, expanding the data set. There also, the results were really a significant jump from what people were able to achieve 10 years back. Now there is indeed a significant, you cannot undermine deep learning. There is indeed a good jump it has got. Similarly, this is related to chest X-rays, where they are finally trying to find out airway leakages. And another important application is diabetic retinopathy. So for the retina, they have taken somebody to in a higher hospital to check the retina and other things. Again, a very good data sets are available there. Some the results, accuracies, robustness they achieved is really good. And again, there are other applications also. Like this is about the prostate segmentation. This is about metastasis in the breast cancer metastasis. And I think these are histopathology images where they were doing some breast cancer related thing from the sample that they have taken. These are skin lesions. Again, there is a very nice Nature paper on that where you need to click a photograph from that they will be able to do the classification. And since they made it in that mode, they're able to get pretty good, very good, very big data set and good accuracies. And also, bone suppression is another interesting area. Okay. So I think let's not dwell more upon. It is no denying that deep learning has caused a significant improvement. The results are no more what we had 10 or 15 years back. At this area, we will spend the rest of the things about where some of the areas where one has to pay attention. Maybe if you plan to work down the line now, in the next 10, 15 years, in the long term you want to work. So I will take a few slides from Jain Harisarsar from IISc Bangalore. So he first says again data science. I forgot to tell about data science earlier. This also falls under into the same category. So they say data is the new oil. Somebody would have also told it. Okay, with all due respect, yes, that is what there is no denying. As I said, it is important. But the way it has been said is, if you have data, you are done. Give me big data, and anything can be done from there. So that's what they mean. Data is the new oil. new quantum mechanics. So classical mechanics was there. Quantum mechanics has almost like overpowered that. So this is the new quantum mechanics. Okay. And then ABCD. People say anybody can dance. No, you say you have in 3 months, data science in 3 months. Your salary will be 10 times. Yeah, so you are starting the name, anybody can do DS. That's what people are saying, right? All the institutions, you in every street, probably in Hyderabad, in some areas, you will have one DS. Anybody for doing DS will be there. So is that true? Okay. So maybe since you have been already studying on that for the last 5 days, data science, this word, how can data have science? Data is there. Science, we all know science, right? Science, we have been taught science in a different way. How can data and science can be related? Why do they call it data science? So then you would like to try answering this. Why do they call this as data science? Now you have this, you could have been very well told that this has been machine learning instead of saying deep learning. You could have even told it data science also and its applications, you could name it.
The study of data as in other science, like other subjects which takes
Where are we studying? Maybe in the very beginning in CNN, people started, they proposed something and they said in neuron also works like this. We got, we imitated that. That's where the science ended. Right. After that, none of these transformers and all these things, see, we are not inspired, we are not biologically inspired in doing something. Why do they call it as a data science? And you have, I don't know what is the name here, so don't take offense, but the branches are also like AI in data science. Nobody knows what is AI and how is it different from data science. Why, how come there is science in data? Where is the science in data? Even online people can give an answer. So,
Yeah, please, you may also respond. Online
unless it is
participant.
interactive, I think it's very boring to be the last one. So it's only means that what they did say there is to say that we use a scientific approach to deal with the data. There is no science in data. Just be clear with that. You still use the word. Thanks again. This is what Professor Narayana sir, until he mentioned, I also never thought about it. How come science and data are clubbed together? Data, even the word data means it need not necessarily contain information. Calling it data is like calling a forest a wood. A tree means it has a life. A wood means it is dead. Right? I am running, I am walking in the woods. If you are saying it, you don't realize that it has life. If you are saying I am walking in among the trees, it is different. So calling it data does not necessarily should have some information. So that anyways, I think we are any deviation. So we will come back. So this is like data. It is the emphasis. So
there is a one response. So I would read it.
Yeah, sure.
Goal of the data science is to gain actionable insight, make data-driven decision, and solve real-world problems.
Yeah, we hope to solve, but again, the data science, the science, there is no science in it in the conventional way. What it means is, as here, you use a physical or mathematical principles. It is only scientific. It is like, while you say science, it is not the science. It is only using some scientific approach to study the data. That's something should be there at the back of the mind when we talk about data science. Okay. So again, that's what it is. And again, what one should pay attention to is the importance should be there on the scientific methods that we use, and just grabbing data all around. Even now, if your guide asks you or if your supervisor asks you to do some project, it's not like downloading all the data sets available, just like we are downloading movies to watch later. It is one has to understand this, look at the scientific methods first. So that is where the emphasis should be there on the so-called science, although there is no science, scientific methods, understanding them rather than the data. That is one thing. And this is again a very nice quote from a Nobel laureate who says, if you torture the data long enough, it will confess to anything. Okay, just like the third-degree treatment for somebody who is there in the jail. So you may change your hyperparameters, keep on changing them. This network doesn't work. Look for more GitHub code, put it and say that that is not working. Nobody knows. The guide doesn't know. The student doesn't know. He says that there is a new method published. We don't know. We just bring that black box there. Start feeding that the data and see what you get. Finally, learning parameter somewhere. If it is 0.01, it will work. You make it 0.015, it will stop working. Okay. So you torture it enough, you will get the results. So that's should not be the way you do it. Okay, so again, let me take one example from this paper in this MRI related journal. What they did is a simple thing. Initially it will look trivial, but you will realize later this does require some attention. What they did is they took images of pizzas. Okay, and then this is called an MRI image. In that a particular even weighted MRI is there. What they did is, I give to my network a pizza image as an input. What it should give me now? Diffusion weighted image as the output. And they train this network, and finally, and the other way also. You give that, and you should get a pizza. I don't know why you do the other. Of course, I also don't know why you do this also. But the network what it can do, it has no idea. You give him the input, you give him the output, and it will learn how to generate the other one. So, is it the right thing to do to get a scan there? Definitely not. But now, this might look to you like I am taking an extreme case, but look at this. For a patient, there are different modalities depending on what needs to be diagnosed. People will take CT, there will be diffusion weighted imaging. For example, inside the brain, the tissues contrast will be very good in MR. Okay, MR is expensive. So what people say, give me CT. From that, I will generate MR. Okay, I'm not kind of exaggerating things. You will find out hundreds of papers where they do it. But if I show the pizza one, it looks a kind of a trivial one. What one needs to keep in mind here is, it might work, it might do something very close to it. But suppose if there is a tumor here in the original diffusion weighted image, from whichever you have synthesized, how it is synthesized, you are giving a training data. So in your training data, if every training data has a tumor, in the synthesized image, the tumor won't come. You cannot take MR scan, maybe because it is very expensive. The proper scanner might not be there in the vicinity. It takes more time to kind of acquire that. Maybe for these reasons, if you want to do it, I have also a book which exclusively talks about image synthesis, where this has been done as well, one of the applications. But unless we understand the physical principles of whether we could get from this to other, does it have all the information associated with diffusion weighted imaging in the CT imaging? If that is the case, then I could attempt that. If it is just a transformation that I need to kind of learn, the network needs to learn, that's one. So, well, you will get some results, but you need to, this is one of the first thing that I would like to draw attention to is, make sure that this is again in the medical imaging I have given. I don't know, maybe one of the things it has come on at the generative adversarial networks, where, for example, you give a satellite image. From that, getting a label of something else, not satellite imaging, but a Google map, like a plain map. So first thing we need to pay attention there is this possible? As a human, if you are able to do it, that's fine. So probably that makes sense. If I give a satellite imaging of buildings and all, I can get a street map. But what about giving a street map, and if I'm giving a normal map and asking it to get a street view, definitely something is wrong. Any building could be there. So this is where something, is it first physically making sense? Is it intuitively, if, as a human, if we can learn and do it, then we could ask the machine to learn that. So that's where, and is it compatible with the underlying principles of acquisition of the data? Yes. So this is one thing I would like to draw your attention. Second point, COVID has happened. Everybody is staying at home. So what happened? There are no home thefts. Where will they come? Like they go out, they have access and they get. So what happened as a result? The number of thefts, home thefts have decreased. Now, people have no other activity there, no socializing and everything. So people went into a depressed mood. Also, the situations were such that everybody's near and dear has passed away. You don't know, a lot of uncertainty. So the depression cases have increased. Now, if you blindly give the data to your network, make it learn, is there any relation between the thefts happened versus the depression? What would be the conclusion here? They will be correlated, and you may end up with the conclusion that decreased number of thefts would result in more depression of the people. No? That's what it will learn with the correlation. And then if you, then the deep learning network will recommend you, how should I come out of depression? Ensure that more thefts happen. Correct? So one should pay attention to, one is causation and another is, as you rightly said, the correlation. So this, unless, is it a cause? Again, I think the time series and all, some of the presentations might have emphasized on how you find out correlation versus causation. So that is one of the very, very important things, even in medical imaging, when you are trying to learn from the data, some relationships, okay? If the visual, if my emotion is so and so, it will see a response in so and so part of my brain. There is also this correlation and causation is something which led initially, there are huge amount of literature which later found is wrong. Don't think that everything that is published in a journal or a conference is the last word. No, things keep changing. And this is one such example. This you would see just because of correlation versus causation, or because statistically it is not significant what you have found out. It might be sometimes due to the errors in implementation also it might happen. But this is something, correlation versus causation, something one needs to pay attention by using machine learning and deep learning methods to learn something. Okay. Right. So other third thing I would like to draw your attention to, the explainability. I guess maybe you had some sessions on explainability also. This is very, very important, particularly in mid. Of course, it is important in other areas as well, but it is even more important, I would say, because it's something to deal with humans. It's not just a kind of a share market. How is it something going to increase or decrease? This is something more serious. So, for example, if somebody, so it is giving you some inference, but at the end, who has to take the decision? Rightly, the doctor, not the deep learning. But if the deep learning method just tells that this patient has cancer, so why you come to that conclusion? Some inference, unless we also get what led the algorithm to come to this conclusion, has to be presented. And without that, because at the end of the day, rightly so, the doctor is responsible for whatever the treatment he has to do. So explainability to that results is very, very important, not just getting some results. So as you could see, the trend is flattening down now, and now the focus is more on these areas. Now earlier, there is a mad rush because there were some algorithms proposed in NLP, speech, and then in computer vision. And once they are brought here, there is a significant improvement of 10% and 15%, which was not possible with conventional algorithms. So everybody is now who will plug in the data into the black box first and get the results and publish. Now the trend is not there anymore. Now people started looking back. Yes, well, it is giving me good results, but how should I buy this? Even if somebody says, even a financial one. So it is saying that don't give loan to that fellow. He has all the information about it, it is given. Now he can show him why. You tell me why you arrived at this conclusion. There were very interesting kind of articles also written on that. There is a discrimination coming, maybe racial discrimination, or the data itself is skewed and hence it is giving that. Unless this is there, every sector now, explainability is something, if you are going to work, is another very, very important area to look at. Even for a treatment also somebody is suffering from cancer, then all the data of how patients are treated all over the world is fed, let's say, to a deep learning algorithm. We told you follow this, but there should be some intuition also. Why? What led you to do this? Unless it is there, the doctor would rightly go for a suboptimal solution than this. So, yeah, this is a consensus journal from January 2023 to give you a little more better idea and clarity on what we mean here by explainable. So earlier, suppose you want to say COVID. Now again, sorry to have too many COVID examples, not many of the second. We'll start the COVID here. Okay. So earlier, suppose if it just tells that he is COVID infected, how do we know the algorithm is correct or not? He is in a, you cannot take, the doctor cannot take a call. Rather than, suppose if it is saying that, see in the image, these are the areas which led me, or increasing my weights or whatever, you said that these are the areas that have led for arriving at these probabilities and this decision. So this is way you said this is one way of explaining. You will show the regions there. Or grad camps, some of you, if you are using just one layer before that, if you take the weights and apply a threshold, the class activation maps would give you some information on whether you arrived at this detection or classification by looking at the right regions. Now again, a lot of research is going on in that area, and that's definitely one area to do for. Even better, there is another kind of explainability is I not only will be saying that these are the regions that led me to that, and also what I will do, I will pick up the most closest cases from the entire training data set. And I will tell, look, you have earlier in the training data set you have given to me, you have marked this person as a COVID infected person. And I see this image being very close to what you have given me right now. And based on that, I arrived at this conclusion. So this is a little more, one more layer of additional information of explainability based on the annotated training data that has been given. Okay. This I would say among the 3-4 topics I would like to say. This is the third important one is the explainability. And the fourth one, the last one in terms of these topics is training versus your testing. Okay, I want to detect the presence of bananas, or I want, don't ask me why, I don't know. I want to count. Again, I don't know why I want to count. I have trained the entire thing on this small my training data set is. I catched a Badiwala who is sending them. I took pictures from all angles of that and I tried. But in reality, this was what I have been given. What do you expect your algorithm to do? What should be a sensible reaction could have been? Could be. Now you train the whole thing on these yellow bananas of the same shape. Now you have testing time, one after the other, all of these things are coming. What should the algorithm do?
Ideally, it should count all the.
Counting is different. Before making any inference, what should the algorithm do?
It should identify the elements which are similar to the training element. And then it should segment them.
Right. What about the rest when it comes to? When it has to do on this, for example, this one, what the algorithm should do? Should simply say, well, I haven't been tried on this. This is a sensible response from an algorithm. This is an out of distribution for me. Out of syllabus, we say when questions are given to us, this is not taught in the class. Don't ask me on this, I'm not going to answer this. In the same way, the algorithm should say that this is an out of, I haven't been trained on this distribution. I am seeing it for the first time. So this is what the out of distribution again. You will see these days a lot of challenges happening where you very close to this topic, although not exactly, is uncertainty estimation. I'm not sure whether you had some on that. You say, how certain are you with your prediction? I will not only say, this is banana, I will also say, well, I think this is banana with a certainty of 20% only, not 100%. Certainty estimation. And also in medical imaging, what we do, Suppose there is an abnormality upon which you have never been trained, or you are not able to learn from that, although it might be there. What you would expect the algorithm to say is, I leave the decision to the clinical expert. I have no idea. This is again a very, very important emerging area in this deep learning, where particularly I'm talking about in clinical imaging, and I'm sure it will be equally important in other areas also, where there are already publicly available data sets and challenges again, where you need to say the certainty estimates, and you should know when to give an answer and when not to give an answer. And so, quantification of that. So, how confident you are in that result. Yeah. So, yeah, with that, these are the those are the 4 topics in the interest of the limited time I wanted to highlight. So, if you have any questions, this is a logical break before I go further, or else I know I won't be surprised if the online people have no questions. Already it's the last one.
We see many times conflicts like how our model is using platform on outside distribution. They say our model is generalized.
Correct.
They say for that. So what do you think is the right way to measure the generalizability?
Generalizability is a very tough problem. On one side, that's the trade-off that happens also between the accuracy and also the generalizability. The moment it is more kind of generalized, the accuracy also takes a toll on that. So that statement that our model is generalizable in a very abstract way should be taken with a pinch of salt, and say now I think something like doing some out of distribution studies and telling that this is what you get are completely unseen data. Now the good thing is even the challenges, it is for this reason. Earlier the trending challenges used to be they used to provide the testing data with hidden ground. Ground truth is not known. Testing data.
Sir, but
That to computer vision, if it is just cars and people, you can count yourself. Nobody has to give us. Even for an expert, even if that is not so trivial to figure out what the ground truth is, you submit your results 4-5 now, you do 10 rounds, at least one will hit like a lottery. So that you could submit if it is allowing you 10 submissions. But hidden ground truth and these experiments now, I think, although not everyone might be working in this is how people are taking care of this. So to say generalizability in that context, what I would say is should be applied on completely unseen data. And of course, testing is of course in some way unseen, but that making a statement that this is generalizable requires some comprehensive experimentation, saying that, let's say, if I have to say from the medical context, this has been done on a GE scanner. Now we are using from a different site where Philips scanner is used. These are the images. I applied there. This algorithm is able to do it, which means the features which it is extracting is independent of the kind of scanning parameters used or the equipment specific or company specific. So that is a simple statement is insufficient, is what I would say.
So I would like to also answer, like I have been working on this, this data distribution, different data distribution domains. So means, let's say, so as you have talked, right? So once if you have trained from one distribution data, and when the time of testing the same class, but you are using the different distribution data, maybe the resources or the way the data has been taken may be different. So in order to overcome this distribution between the training and testing set, so a lot of algorithms have been proposed, domain adaptations and transfer learning. Those algorithms have been proposed. So even like I have also contributed 5-6 algorithm in this. That is my core area, means out of distribution data that I have been working on those things. So so mostly what the people they usually do. So maximum mean discrepancy, that there is a one loss function is there. MMD usually you call So that basically they use in order to minimize the distribution gap between the source as well as the target. So there is one more is the choral loss is there. Means it is a second order distribution basically we call it. So in order to tackle all this kind of problems, so specifically there is one area. So I would suggest you to means prefer this domain adaptation. So now domain adaptation here is recently the paper has started coming on this medical domain as well. Okay, so
it's like getting more deeper features
yes,
which are independent of all these variabilities that happen
yes,
on the surface.
yes. So even like if you apply this kind of MMD first order movement or second order movement or higher order movement, HOMM are there. So of course, like you would be able to improve the performance of the model around like 30%, 40%, and 50% also. That I have done also. So that we introduced. So what in the experiment, what we did, so we have taken some images from one domain, let's say from DSLR camera, you have taken right images and you have trained the model. What if the same classes images, if you have taken from the low quality images or some night background, right? So same classes, but due to the environment or due to the resources from which the data has been taken, so it may be different. So because of that, there is a distribution gap between the source and the target domain or training or testing data. Okay, so in order to overcome these things, so these kind of parameters would help a lot. Maybe it would be applied, so people have started working on those areas also. So there is also one question in the, okay, I would read it. So for uncertainty estimate, the model saying it is out of distribution, how would we train our model for it? Would we just use the softmax score or see it's neither too low or high, so uncertain, or we are going to add additional class for uncertainty?
Again, I'm not maybe, I think I more or less understood. So how to get the uncertainty score, I think.
Yes.
Again, there are quite a few methods
Yes.
that look into based on the inputs that is getting, it will essentially try to find the distribution
Yes.
of this and tries to compare where exactly this sample fits.
Yes.
One simple trivial example in a one-dimensional case we could consider is, let's say there is a mean and assume that it's a Gaussian distribution and you got the mean and variance here.
Mhm.
Now what we look at it is where exactly is the sample falling.
Yes.
If it is close to the center of it or where there are a lot of samples,
Yes.
you are more certain.
Mhm.
The more it is falling into the tail part,
Mhm.
then you are less uncertain about it. So again, it can be based on that, it can be quantified in some sense. I think I'm sure quite a few variants of that will be there, and also given that it is
Yes.
a multidimensional data, one needs to figure out on how they do it, but essentially this is the idea. Yes.
So yeah, Brother Goshia, do you want to ask any questions as you raised the hand?
Yes, sir. I actually was about to ask the
1
same
minute.
question. How we can handle this OOD problem in this computer vision out of distribution?
Yeah, could you ask?
Hello. Yes, sir. Am I audible?
Yes, you are audible.
Sir, I'm asking that how we can handle this OOD problem in computer vision while we are dealing with the computer vision problems.
Which
How we can
problem?
get computer vision problems, like in medical imaging, how we can deal with OOD data.
Hello, is it out of distribution?
Yes, OOD means out of distribution.
Yeah.
Again, I think the lot of developments. Yeah, I think lot of developments are there in the computer vision area itself. They are coming, quite a few breakthroughs are coming there itself. So you need to look into the literature there. Again, I'm not somebody who is working into it. I'm sure there will be a huge amount of literature on that. Recent literature, you could have a look into that for the exact specific methods to look at. I do not know any specific thing unless the problem is also known. So that will be difficult to even suggest something else.
Okay. Okay, sir. Thanks.
Yeah. Yes. Okay. Good. So maybe we'll move on to the next part of that, where I some of the works that we are doing there at IIT Tirupati. So these two are my PhD students who submitted their synopsis and their answer now. He is one of our MS students, and these are all the MS students that have already completed their MS, and BTech students and MTech students as well have contributed to some of the results that I'm going to show here. And if anyone of you would like to, this is again you could think of as the marketing that I'm going to do for my lab. If you are interested, you want to have a chance to do your MS, most welcome. For those who are doing MS, if you want to you are looking for PhD again, consider applying to us. And yeah, BTech guys also, if somebody is seriously interested, you can approach us for a, maybe if it is possible, BTech project, provided you are serious about that. Please do drop an email. It will be there with the, I think with the presentation, you could have a look at that. So again, maybe 5-6 problems. I will only tell about what is the problem we are kind of addressing, rather than going into the details. Will be boring. So I'll just mention the problem that we are going to solve. So something we work in the CT imaging modality a lot. So CT image, I'm sure you have many of you have seen also. There will be a kind of a table that goes in there. This is called motorized table will be there. The patient will be taken inside the scanner, and it is here. There will be a rotating one, which is referred to as gantry. On one side, we'll have an X-ray source. Exactly on the opposite side, there are detectors. Now, this would be rotating here, so that you have multiple projections of it. And this is a single one is like one X-ray scan that one will get. Okay, X-ray, I'm sure all of us have gone through that. So each one is essentially a 3D object. We have a 2-dimensional projection of a 3D object. And you have it from multiple, in terms of multi-view projection, you could think of in computer vision. So you do have the multiple projections of it here. It's happening. And from those multiple, the original object is 3D. You have multiple 2D projections. And from that to reconstruct the 3D object. By reconstructing it, you would get a CD essentially. That's what would happen. So all of you have seen, and the scanner right away gives you this CD image, which you see down here. But what the image captured is in fact a different one, as each projection is happening here. For each angle, these detectors have the value. So on the x-axis, you have one projection angle, and for that projection angle, the detector responses, which is an accumulated value of attenuation coefficients of all tissues that come on its way before it reaches to the detector. So this is what is referred to as sinogram. What the image, what we finally see is the CT scan. Essentially, this would, if you look at that, then what you do is, this is called as a back projection. You do it, and then from these multiple sinograms, you reconstruct the scenes. This is the CT reconstruction. That's what the machine gives. So this whole process of acquiring sinograms will hardly take few milliseconds. So consider 1 or 2 seconds, considering the real time setting up and doing all this stuff also. Then most of the time, depending on the sophisticated algorithm that you are using, based on the type of projection, again, there are different generations of CT scans, which I'm not going to take. This can go up to 30 minutes, but this would happen in just a matter of few seconds. The idea is this. Although the current trend is to do the diagnosis based on CT images, you could see here, there is, after all, what it is, there is a transformation that is happening from the sinogram in order to get the CT images. Correct? Here I have projections from different angles. Each one is this way. From that, the spatial information I am decoding from here. So, since deep learning methods are known to extract the latent features, can I right away do detections and everything from here? Okay. That's problem-wise is good, but application-wise, we need to somehow justify this. So one way of justification is that there are quite emergency cases like traumatic brain injuries, where suppose if we know that there is an injury, from here itself, if you are able to do from sinogram itself, the rest of the, you could think of one doctor being there and some 10 patients have come, which is not uncommon, at least in India. So whom should I attempt first? For a doctor, this is not human interpretable. We cannot say, by looking at it, this image, if you are able to say, you are in a, we need such people, so please let us know if any of you drop an email immediately. Okay, so that we cannot do. This is not human interpretable. So no one has attempted. It was not there yet. Thanks to the developments, you could learn the inherent latent features. So can I do the detection? So this idea resulted in one thesis where this went done, and she had day before yesterday was her synopsis, and this is the main idea. So what to get some intuition, a little more intuition on why this could work. Can we see some patterns here in sinogram also, although we might not spatially tell it? You look at it this way. Suppose you have an object here. Consider this as some attenuation coefficient values are represented with color. What would happen there? When I take a projection here, what would happen? The value here is more. When I consider that I am summing up all the values that are there on its path before it reaches there. It's an accumulation of all attenuation coefficients. So you could see something at this angle. Since I could have represented with intensities, but since intensities, to make it a little more intuitive, we are just keeping as if that is a profile of it instead of intensities we are talking. Now, the same thing I have taken, I take the same object, acquire a one-dimensional projection of the 2D object from different angles. Suppose that 45 angles if I take, that's how the projection would look like. And I take multiple projections in this angle I take. So essentially, when I have an object there, I could see a pattern like this. That means there is indeed a pattern that you could see here, which if your deep learning algorithm is able to learn, you could do right away the diagnosis from here. Of course, training time, this is expensive. It will take maybe a few tens of hours. But once you are training it, this would give you hardly 1 second is more than enough to get results from a trained model. So that's the basic idea here. Okay. So again, that this is something that got recently published in Medical Physics Journal in September 2023. So it has two things. One thing is, how does a doctor look into a CT scan, for example? In CT scan, the values represent something referred to as Hounsfield units, which has a range from something like -3000 to +3000. Depending on, he knows how much attenuation will happen when X-ray beam passes through different tissues. Suppose if I want to see the brain part, there is a particular range of intensities you look into, the rest will be made suppressed. So that's referred to as in image processing as you do a windowing operation. He looks at it at some window. Subdural region is another region in the brain. He wants to look at if there is an injury in this region. He uses this particular range of intensity. Same is soft tissues. So the first idea is, can we do a similar stuff to sinogram? Will that, if I do such thing in sinogram, again, the difference is here, spatially we know which tissue is there where, and there is a knowledge about the attenuation factors range there. But on the other hand, sinogram is an accumulated value. So simple thing doesn't work. So it's a kind of, again, a linear transformation is happening there. Can we learn also that in deep learning? If I feed these learned things instead of the original sinogram to my deep learning, will that improve the results? So the results that we refer to as intensity transformed sinogram synthesizer. So we are synthesizing the sinogram. That has considerably improved the results. Now the bar is what are the detection accuracies and all that you would get with the CT image. So with all the different kinds of methods that we use, it is able to now give results that are on par with what you get with the CT image. Again, don't think it as a substitution for a CT image. Of course, CT image comes from sinograms only, but still you need CT for the final call by the doctor. So that reconstruction will be done. Meanwhile, they refer to something called as a medical triage. Triage is like a prioritized queue. You will know which patient to kind of attend first, which is more serious case. You can do that. And also, again, as I said, interpretability is a very, very important thing. Whether is it because by a fluke it is learning, or something else which you haven't paid attention to is helping it to learn. Just now, whichever work you do, and if you want to go to a good journal or a good conference, this is something in interpretability, at least at a very basic level, you should do it. So something like GradCam, I'm sure you might have come across class activation maps, which is a kind of not the best thing to do. Again, this is another very important research area these days. There are many other methods these days. In the interest of time, I won't talk much. But if you plan to pick some areas to work, this is one of the areas to look into. So again, GradCam, the color here, higher the brighter the color. For now, you consider magically you got it. Okay. Once you have it, what we are looking at it is, suppose because of the injury, this is the region we mapped that to cyanogram again. This is called forward projection we did here. So we can figure out here it is indeed looking at the right regions to make the inferences. So this is the least thing that you should do now these days. You are doing some deep learning tests. So with that, I will stop that application talk. And the next is cranial implants design is another thing. This is again a BTech student. Again, BTech students, if we find them motivated ones, they could do a really good work. This work is entirely done by a BTech student. From the third year itself, he started working on deep learning. He wanted to work, and day in and day out, he was working some 30-40 models he has implemented, and finally, this resulted in medical image analysis journal into a challenge. Internationally, it was 5th rank, and I think his algorithm stood 5th at the end. And this average publication time is 1 year. So, although it is not individually went one, this went into that itself is a very prestigious one. So, message is, if you guys are motivated, you can really do many interesting things here. Okay. So essentially here coming back to the actual one, cranial, there would be some accident or sometimes to do surgeries, part of the skull might get impacted, affected. Now, I don't think that you are finally thinking what way this way, that they use a titanium alloy, and if they use it as a grid, but we were just curious to print it also. We wanted to print to get some experience with that. So that's used in titanium alloy. We have people who are there in this manufacturing also. We have a good team there. So medical grade titanium alloy. This is the skull that has been removed. This has been, they have created a data set and has given that, and we need to define it. So that's also we find very good results there. They'll not go there is something called algorithms are there, but these things it is that the deep learning models at a 3D level. So that's something that's right there. And another, this is again another, I just want to say there was another student by name that was Prabhat. It was Ashwat, and this was another student by name Prabhat. He went to vacation with his family to Goa, and sitting in the Goa beach, he was submitting this thing. He is doing only this throughout the day. Okay, that was the level of motivation he has. And again, this is a very kind of 13th, PICA is the conference, which is a very well known, and it is like ICCV is for computer vision. It is there. Workshops are there, still they are of very high quality. So you could get some good work. So again, this work is at a level of there is an imbalance of data. How do you deal with the imbalance of data? There are many nice cost for it is at the kind of loss functions that you use. You could use it. So that's the kind of work he was doing. This is another PhD student that was one Sindhura, one PhD student. This was by PhD student by Sumant. MR imaging also, what you get out of the MR scanner is a complex data. So from the complex data, typically people use the magnitude data. Again, complex means magnitude and phase. That's how you look at it. Typically, to construct the images from the magnitude-based reconstruction you do. But there are some regions in the brain, and there are some kinds of acquisition protocols where phase carries important information. So again, this work is deeper, and then phase gets, for those of you in signal processing background, when you are doing a Fourier transform kind of stuff, there is a phase wrapping is what happens. So you get complex number from that. If you want to find the phase, A plus JB, if I give you, if I ask you about the phase, what is the phase value of complex number, A plus JB? Tan inverse D by A phase. Now that can be from minus pi by 2 to pi by 2, minus pi to pi only. So how do you get, because the phase actual value would have some physical meaning there. So here that's something to do with the magnetization of the tissue. So that's something the work he has done. And this is another work currently under review in the International Symposium on Biomedical Imaging. Is not all works have to be such fast, but anyway, if I have a sinogram and a CT, although there is a transformation here, but there are quite a lot of applications where I want to do my job with limited computational resources. And also I might not be, as I said, in medical imaging, one of the key challenges to get data. Suppose I have this amount of data and with least computational resources, I want to do this. So the idea was this, to extract features separately from sinogram and as well as the CT, I combine them. And let me use a lightweight architecture here. Will that improve my overall things compared to the sinogram and CT integration? So that's the idea. So yeah, pretty good results have come. There is a significant improvement. Not only that, intuitively also it is making sense. For example, the diagnostic accuracy from CT, for example, if I look at it, this is the lesion here, which has been inserted here. CT-based method is giving with a probability of 0.26, is saying it is a tumor. And sinogram is telling with a probability of 0.47. But when both are combined, the probability is going to 0.9, because essentially you are learning patterns from CT and learning patterns from sinograms. Individual patterns might not be enough, combining them is good. But of course, if you use a very big network, after all, whatever is there between sinogram and CT is a transformation. You could in fact learn that transformation there as well. But this makes your job easier when this makes your job easier when. So that's the idea here. And yeah, this is something very in India, a couple of conferences for those of you who will be working in computer vision. In India also two well-known conferences are, one is ICT-GAT and another is ICCD, so International Conference on Computer Vision. So it is by the master student Sasigar and also another PhD student by name Vaishnavi. There is something called as wireless capsule endoscopy. So what they do is they want to get whether there is any bleeding happening in the intestines. So there will be a capsule like this, which has a camera and properly encased there, and it has all these transmitters, battery transmitters and everything. Just the patient needs to swallow, because doing endoscopy till here is fine, but going inside within the intestines, if there is any injury, with a normal probe, it is not that convenient to do that, or even not possible. So they make him swallow, and finally it comes out. That is harmless in a way, mostly. So this is how it happens. Just will be swallowed like you are taking a medicine capsule. So then there will be not less than kind of 57,000 to 1 lakh frames of 6 to 8 hours. It is taking pictures. For a doctor to sit and see 1 lakh frames is pretty time consuming, and also they call something as fatigue of the eye. So by the time the actual one comes, he might miss it if there is a bleeding also. So can we do it in a deep learning? You use whatever method, not necessarily deep learning, whatever, you just give those frames where they do observe a bleeding. So that's the problem definition. Yeah. So I think some of you might have now, even transformers have been covered, I think, right? Yes. So he used the swing transformers here. He's doing, see, first thing is, I keep telling to my students is, don't see data as something that has to be fed there to an algorithm. Rather, you better spend a lot of time on seeing and understanding the data. First thing is, by looking at the data, how you are inferring, you should feel, if you are working particularly in medical imaging, while there is no doctor with you, you should feel that you are the doctor and start doing a diagnosis there. What you have a ground truth with you. When a machine is able to learn, why not we? Definitely, somebody who is developing an algorithm should be superior to the machine where it is simply done. So you do it for that in the first place. See then, what is it that is helping you? What is that you are looking there to come to that inference? And can somehow is it taken care here by the algorithm? So you should spend Yes, another one is there. For him, there are CT scanners. The data is 200, even 100 slices. You show him one of those slices, he will say the image patient ID, he will tell. To that level, he has seen into the data. Then only you can in fact come with a better algorithm. You will understand why something is failing. Don't just look at the last numbers of how much sensitivity I got, specificity, AOU. No, not enough. You should see where it is doing well, where it is failing, why it is failing. How can that feature be extracted? How is my algorithm doing? Suppose I'm using CNN. Is it downsampled? And that is a very small thing. Next layer itself, it is you have downsampled the image and there is no tumor there, for example. And are you kind of carrying the features from there? If you are not carrying features from there, you are doing downsampling only in the last layer, you are looking at something, the information is already lost. So that is very, very important. You use deep learning to make use of its power, but at the same time, make sure you have an intuition for what you are doing. So in that you see pre-processing when it is doing well. So he has come up with a different pre-processing, and then detection also might be, you have seen with the YOLO and RT letter. These are the kind of the recent state of the art methods that you find out. So once there is an injury, you would also detect where it is. So again, that's again, as I said, minimum visualization of this thing is also mandatory now. That the least thing that you should do there to ensure that this will tell you these are the really ones on the top row here. It will tell you like where by looking into which region it is able to make inference. Okay. Again, pay attention. Initially, my impression was if there is such region shown, it has to be positive. But later realize it only tells you by looking into which region primarily or predominantly came to a conclusion. But the conclusion could be negative also. Okay, keep that. That's a very, very important point to look at it. For example, this one as something which is actually not bleeding, because that's the kind of food that has been there, or the patient has an impact. But it only tells you which is the region it looked at. When there is no bleeding happening, the map would be showing the entire region in some of the cases. Don't get surprised there. Yeah, that's one thing I will mention. So with that, those are the 6 kind of, I just outlined 6 of the applications we were working on. So maybe some points to takeaways to tell. Particularly in clinical, in medical imaging, how do you incorporate the clinical knowledge along with the deep learning models is a very, very important area. There is some amount of work we are doing, but the interest of time we have explained here. But that's something you need to look at, particularly in the medical imaging domain. And then, as I was mentioning among the 4 challenges that one perhaps needs to pay attention to, looking at causation versus correlation. Explainable AI is another thing I would say, uncertainty estimate, and then of course now having generic. Nowadays we show very good results on, let's say, you train it, test it on whichever a machine is there in one thing, but generalizability, as you are mentioning, is very minimal, particularly the scanners and MR images. So that's also is a very, very important thing. You need not get 99% accuracy, but something 80% accuracy across multiple scanners. This would be good. So that is another very important thing. Now, maybe distributed learning also you might have, I guess, some topics, federated learning, distributed learning. That's also now, even in medical imaging data, I might have some patient's data with me, but I don't want to share with somebody who is at a different site than data, because this has patient data means this is a very sensitive data. You cannot just share with them unless you have permission to do it. It can be exploited in different ways. So what you would rather say, I won't give you data. You bring your algorithm, learn some high-level features and go away. I'm not going to give you that. So if I just first train it on my train that model on my data, then it comes. Then they come to another site and train it. It may eventually get biased by on which data it has been trained last. I'm just giving a trivial example. So how do you deal with it in an efficient way? That's where this distributed learning, federated learning, and all areas will come. And again, finally, for your model to be deployable and to make use, you cannot ask them to buy a system with 10 GPUs and kind of 512 GB RAM and all those things. It should be deployable in a lightweight architecture. And so that's also something that with a minimal deep learning model, with a small deep learning model, you should be able to do a good job, which is almost on par with the best results that you would get in order to make it deployable and practically useful in the day. Yeah, so maybe since it is a deep learning, I thought before I say thanks and questions, this has some debate. You sit with your friends, and if you are seriously thinking about this, these are the questions that will come. Will AI replace the doctors? Okay, or the radiologists? So you all know, I think Jeff Hinton, I think recently some statements he made, at least you would be knowing all those things. So his statement in 2017 is, we should stop training radiologists. That's a very big statement. Okay. And then this radiologist and all, and then this is also Andrew Ng. I'm sure everybody in machine learning would know his name. And we would have done these two courses, Introduction to Machine Learning and Introduction to Deep Learning. This week we could finally pick his speed as well there about the same time when they published something. I think this is on mammographic images. Is this the time you should stop now training all these people? Just have deep learning, deploy deep learning algorithms. The better answer to that will be what has been later discussed. Similar 2017 itself, so all medical imaging community doctors will have meetings and conferences. Oh, people say that should we stop doing it? So more sensible statement is the question should be, there is a problem with that question itself. The approach should have rather been, will AI replace radiologists? Well, not, but radiologists who do AI will replace radiologists who don't do AI. That's a more sensible concept. Although this is in a limited context of medical imaging, this would be equally applicable in other areas also. Now, my ChatGPT or whatever it is giving the course. So what should I do? Well, those who learn ChatGPT, even if there is a minor bug there, unless you know, you first learn and then make use of it. Then you could fix that. Otherwise, you will sacrifice the entire code also because you don't know the Python. You don't know how to fix that bug. You can't go on. Some module it is not giving well. That part you code yourself and use it. So you could extend this, I thought, to other domains as well. So I think more sensible statement would be radiologists who learn AI would replace those who do not learn AI. This is a very good supplementary one.
I'm saying generalized statement.
Correct. So then you can make a very generalized statement. So this is what pictorial way you could tell there. And yeah, you could read it yourself then. So
let's have a round of applause for a wonderful talk. Really, your talk was very interactive. So the participant would have got a lot of insight from your talk.
50% of them already dropped.
No. Still they are listening. So those who are really, interested. So now we would have take some questions. So yeah. So participants, if you have any questions, so feel free to ask. You may unmute your mic and you may interact with the professor.
Yeah.
It's out of the yes, please. So there was a talk about generalization. So how long we are from an era where this one particular model can do all these things, like the general sentience.
Oh, that's a good question. But I don't think I know the answer. I don't pretend to know answer. See, every time, even if you look at when did this started as an in fact, around 1970s and 80s it started. Then it was the rule-based approach started. I think somebody would have talked about this history of this thing. So what people thought at that time is AI is going to replace everybody at that. Nothing had happened. Okay, and then I came to know from another professor, there was a time when you say I work in AI, you will not be given a job. You will be fired. Even if you are given the job, you will be fired. That was the situation because the height given to AI is so high. And suddenly they got disillusioned. Oh, your expectations, it is like you have from your friend, you very high expectations. So when your expectations are too high And on the 5th day, you realize that, okay, this is not what reality is far from that. The reaction will be extreme. Same thing happened with AI. And then even in medical imaging context, people thought that, I was recently listening to one of the talks from an MIT professor. In the 80s, I think, they spent 15 clinician years. 15 clinician years means if a clinician sits for 24 hours a day, and if he sits that way for 15 years, that was the amount of time that has taken for them to create a medical database of symptoms. So they will say this has these many symptoms and that. They created it, hoping that this will revolutionize everything. That is also in a way, that is how AI start to be, artificial intelligence, that way start to be. There will be some symptoms here and there vary, but now I will have a model or a discriminator that will learn which has the maximum one, and even a rule-based purpose good enough. But none of us are using it today. It is in full use. All of that thing is just lying down, maybe produced some papers, and we are not using it. Reason being, later they realize that we might have flu symptoms, even if all of us, okay, God forbid we don't catch flu now, but even if we all of us catch flu here, symptoms will be different for a simple thing as simple as a flu. Now consider if we go to a different country or a different site, it will be even different. What they realized eventually is these kinds of symptoms, and this is good for this database that we have. Change of that thing, this simple thing doesn't. So every time when every new invention happens, we start thinking that this is the best invention, we are very close to it, something else. But one thing for sure is, while it has brought a leapfrog jump to what could have been done without deep learning, there was a lot of exaggeration happened around deep learning. It doesn't mean that we should stop learning and we should start blaming deep learning. No, you should take the fruits of it, but you should understand its role and the. So I don't know whether I answered, but it is very hard to say. You could say application-wise, as I showed mammography, extremely. So wherever there is a limit, if you means essentially what should happen, your algorithm on one side, the data should capture all the variability that is there on one side. Second, as the earlier it has been mentioned by Dr. Rakesh, what should happen is the features that you pick from it should be an abstract feature, not affected by some variations in your system parameters. Whether it is dark condition, bright condition, the feature extracted should be both. Until and so, this is a subjective one. Do I have a data set that covers the entire thing? This is the first question. Is my network is able to do it? So you could definitely tell it for some applications it has happened. All those applications are sure. Now you cannot get away with this. You have to learn. There is no doubt about it. But don't sacrifice the rest of the learning that comes from the engineering domains. Unless you know the signal, you are into the signal processing, you should know signal processing properly. And all other rest of the things also. Domain knowledge, deep learning is not a based method. Somewhat answered. Without answering. Yes.
When I saw some British students, I observed training on medical images. Like having 1,000 images is okay, but each image is really very big.
Correct.
They needed something like 30 GB just to load the data. So, like when you have computational limitations, like not having sufficient GPU or some high performance computing environment.
We can talk. We have systems, so we will. Yeah, that is a very big change. So that is why the focus is on weight architectures. So even the models which we have done, he used to do on this Google Colab. And that has some, I don't know, he has struggled a lot. He created some 3-4 accounts. And once it crosses from 4 hours or 5 hours, there is a limit, it will stop. So we also had struggled a lot downsampling the image, downsampling. But the other participant, they have the full data and they run it. So you are working on already a downsampled data means half the features, half of the data is already sacrificed in a way. So reaching that is a difficult. This is a serious problem. So luckily now we got a DGX machine, 80 lakhs
Yeah,
machine.
we
with
are
us.
also planning to procure.
So that is particularly for medical domain.
Yeah.
It is very challenging. But at the end, it also should be, that is where the domain knowledge also can be helpful. For example, let's say in a Fourier domain, we might have a better representation of the system. Or can you already extract some well-known features and let the deep learning algorithm learn the deep features from it, rather than entirely leaving the job at the mercy of the deep learning algorithm. So that is where I think the progress should eventually go. And even if we want to make it deployable at the end of the day, that's how it should be. That's the very, that is where, that is not the ground where we should compete with the industries also. They have no issues with the amount of computational facilities that they have. They could use, and data is also, we can never compete on any given day with the amount of data that they have with them. So if we want to publish, also forget about even deployability, we should kind of face them in a different ground. Where, for example, how do I embed some prior knowledge about it? So slight redefinition of the problem that we want to solve would help there. But again, not always possible.
Yeah. Now it's the game of rich and mighty.
Correct. So that is why earlier it was not the case that research was happening so much in industries. Now, where is the deep learning breakthroughs are coming? Yes, Facebook, Google, Apple also is coming now, and all this, Intel, you name it, NVIDIA, everybody is onto it. Now, as a researcher, as an academician working, we should find out some alternative problem definitions, not in terms of the AlexNet they are using and other architectures. Very difficult. 1 million images, where do we train and when will it come to?
Yeah.
So that's another big problem. Some of the algorithms will run for 3-4 days. Then we will realize that hyperparameter I haven't set properly. That hyperparameter I have to change it. And then only after 5 days you will see what is going to. So I think that should not be the ground where we define our problems.
Thank you.
So audience, if you have any questions, so please feel free to ask.